Welcome to the measurable functions. Today we will study the definition of measurable functions and their simplest properties. But before starting this chapter, I want to recall our previous lessons. We talked about measurable sets, the inner measure, upper measure, outer measure, and also the measure of bounded open sets and closed sets. If please watch the previous videos to remember to have some basic information about the measures, and if you have any unclear if you have any questions, any unclear parts, please let me know. And let's start. So consider that E is a set, a subset of real number set, and fx is a function defined on the set E, and A is a real number. Let's introduce the following notations. Let E be a set of x such that fx is greater than A if f is greater than A. And also let E be a set of x such that f is greater than or equal to A if f is greater than or equal to A. And also the third and similarly the fourth notation, if A is let E be a set of x such that fx is equal to A if f is equal to A. So for the given real numbers A and B, the following notations are also true. Let me write for the given real numbers A and B. Then E, the set E of x, which satisfies this condition, if f is between A and B, less than A and less than or equal to B, then E is a set of x such that A is less than fx and less than or greater than B. We can also define E A less than or equal to f less than B. And also we can write it similarly, x from E, A is less than or equal to fx and less than to B. Also we can define E A less than fx less than B. I will not write it. This is similar to the previous examples. And also E A less than or equal to fx, and this is less than or equal to B. And we also will consider that the mentioned function, this function, can take values minus infinity and plus infinity. Let me give the definition. Consider that fx is defined on measurable set E, that is the subset of R. If for arbitrary finite number A, the set E is measurable where f is greater than A, then we say that the function fx is measurable on the set A. From this definition, we can easily see that the function defined on a set of zero measure is also measurable. What does it mean? What is zero measure? Zero measure is the set like that. We say that the measure of this set is the subtraction of endpoints. Yes, the subtraction of endpoints is zero. So this is the measure of zero, and this is the measure of zero measure, the set of zero measures, sorry, and let me write it. We can easily see that the function defined on a set of zero measure is measurable. If we define a function in this set which measure is zero, then this function is also measurable. Theorem 2. If f(x) is a measurable function on set E, then for arbitrary number a, the following sets are measurable. E, where f is greater than or equal to a, where f is equal to a, where f is less than or equal to a, and where f is less than to a. Also, if a function f is measurable on a measurable set E, then it's measurable on any subset of E. And it's obvious that any subset of a measurable set is also measurable. So if a function is measurable on a measurable set, and then it's measurable on any subset of this set. Theorem 3. Assume that the function f(x) is defined on measurable set E, and E is union of finite or countable number of measurable sets ek, which is denoted like that. E is equal to the union of finite or countable number of measurable sets ek. If f(x) is measurable in each set ek, then this function is measurable in E. Let me give you some examples about measurable sets. The first example is the constant function. The constant function f(x), which is equal to c, and which is defined on measurable set E, is measurable. In fact, the set E, where f is greater than a, is equal to E itself if a is less than to the c, and it's equal to empty set if a is greater than or equal to c. E is measurable as it's given, and the empty set is also given. And consider another example. Consider that the closed interval AB has partitions as A is equal to, let it be C0, less than C1, less than C2, and it keeps going, less than Cn, and it's equal to B. And each interval ck plus 1, fx is constant in this interval. Let me write in each interval ck plus 1, fx is constant. By theorem 3 and the example first, the first example, we can say that, let me write, by theorem 3 and example 1, we can say that fx is measurable. And theorem 4, let me write. The function fx, which is defined and continuous on the set E, the closed set E, is measurable. I will not prove this function, and I want to give the final theorem and finish our today's tutorial. So, theorem 5. Consider that the function fx is measurable on a set E. Then the following facts are true. The first fact is that for any x from R, the function fx plus k is measurable. And second function, the second property, for any this is k from R. For any k from R, the function model fx is measurable. And k times fx is measurable. The third property, f squared x is measurable. And our final property is for any x from E, if fx is non-zero, the function 1 over fx is measurable. I will not prove this theorem, the properties, the facts about these theorems. If you have any question, please let me know. I will make a new video also about the examples of these theorems, and I think it will be clear for you after these examples. So this is this video tutorial I need I think need practice. So if we practice this theorems, I think it will be clear for you. Don't be afraid of the words, don't be afraid of the theorems. Please let me know if you have any unclear parts. And that's all. Goodbye. See you in our next video.